All right, sports fans, we are in the home stretch here, part 6 on neutron detection. And here we're going to be talking about slow or thermal neutrons in chapter 14. We say the only methods for detecting neutrons are indirect and must result in the creation of charge first. This means that absorption is the only type of interaction for detection. Now that does apply mostly to thermal neutrons, because when we get fast, we know we have a few other mechanisms that are available to us. For slow or thermal neutrons, there are only 3 materials that are widely used: helium-3, boron-10, and lithium-6. Always consider the reaction products when determining what the signal looks like. So we have a few straightforward equations that we are going to use. We have this thing called cross-section, and we have a macroscopic cross-section. My macroscopic cross-section is represented by capital sigma, and it is equal to my number of absorbers or interaction atoms times my microscopic cross-section, which is, of course, a function of energy. We know that there are 6 different types of interactions that we can have for neutrons, so I'm going to say that sigma total is the sum of all of those types. So we have the macroscopic cross-section for elastic scattering, we have for inelastic scattering, we have electromagnetic interactions, we have charged particles, let's see, we have neutral interactions, and we have fission. So those are our 6 interaction probabilities. We know that the mean free path, lambda, is equal to 1 over the total macroscopic cross-section. And we also know that the energy of my neutron, this is based off of the Maxwell-Boltzmann distribution, so the energy is actually an average, and that average energy is a function of what we call the temperature of the neutrons, and that's 3/2 kT. Lastly, let's talk about the efficiency as a function of energy for a neutron detector, and let's say it's for absorption, because that's the interaction mechanism that we care about for thermal. So my efficiency as a function of energy is 1 minus the exponent of the negative macroscopic absorption cross-section as a function of energy times L, which is the path length through which the neutrons would travel in the detector. Couple other quick equations here when considering thermal neutrons. Remember, we're going to have an absorption event. We're going to have 2 reaction products. We'll say reaction product 1 and reaction product 2. We know that Q is the energy that is available to those reaction products as a result of the reaction, and that is going to be shared between, it's shared energy between the 2 reaction products. We can use conservation of momentum and conservation of energy to work out which one of those 2 products gets how much energy. So we would say M1, we'll call this little v1, equals M2, little v2. We could also say that the energy of either of those products is P squared divided by twice the mass. So those are the equations that are going to describe our thermal neutron detectors. But not least, we have chapter 15, which is fast neutron detection and spectroscopy. So when the energy of the neutron is on the order of Q, that reaction product energy, you can actually measure the energy of the neutron by measuring the reaction product energies. It is not lost like in thermal neutron detection. Number 2, once the energy of the neutron increases, the energy transferred to a recoil nucleus becomes significant. This energy can be deposited and measured and is the basis for neutron spectroscopy. So now we're talking about reactions such as collisions that actually can be used for detecting neutrons, unlike thermal neutron detection, where the only thing that we could use was absorption. So let's talk about what the energy is that's deposited in the detector. So remember, our requirement here is that the energy of the neutron, is on the order of Q. Here now we have E sub T, which is the total energy deposited, is equal to E sub N plus Q. Or we could say E sub t minus q is equal to the energy of the neutron. So by measuring the total energy deposited and knowing the q value, that's how we can back out the energy of the neutron. When we start talking about measuring recoil products, though, now we're going to talk about scattering. And remember, we had two different frames of reference for scattering, the center of mass frame and the lab frame. So center of mass is going to be represented by capital theta, and the lab reference frame is going to be little theta. That's the scattering angle in those. And so we have the energy of my recoil is equal to 2 times A, where A is the atomic number of the absorbing detecting material, divided by 1 plus A squared, times the quantity 1 minus cosine of capital theta, times E sub n. We can also use reaction kinematics to work this out in the lab reference frame. So this is also equal then to 4A divided by the quantity 1 plus A squared times cosine squared of little theta times E sub n. Okay, so those that recoil product can also be used to uniquely determine the neutron energy if we know what the scatter angle is in either reference frame. Thank you for participating in the online NPRE 451 final exam review. Good luck on your final, and remember, the charge, the charge, the charge.